Today we are going to look at Bayesian decision theory. But before then, I want to do a bit of recap on what we covered, or some of the concepts that we have covered. And this will help us to be ready to do our CAT. Because given that we have to do online CAT, I decided if I give you a CAT up to a certain point, it may be a bit difficult to set such a CAT online, because it might only involve maybe finding the posterior distribution, especially some of the distributions, and you give your answer in terms of the distribution function itself. But because I intended to give you a CAT which is mixed, both maybe some multiple choice questions and some numerical type questions, then it would be important for us to cover whatever we are going to cover today. Then it will be possible for you to do at least some good work in the CAT, and then also CAT 2, of course, again, will also be a bit comprehensive, and that will help us now to be able to get prepared for the semester examination. So I want to do a recap using a scenario where you have the binomial data, because when I have a question like assume that the prior distribution for the proportion of defectives, as long as it is proportion of defectives, meaning there are only two possible outcomes, you either have a defective item or a non-defective item, so it means this will be binomial. So if the data is binomially distributed, and then you are given whatever kind of a prior, so like now this one, the prior here is a discrete case, meaning here I have both cases are discrete. The data is discrete, the prior is also discrete. So we'll handle that one. Then we can combine the same data with maybe a uniform prior or rather a beta prior. And then we try to see maybe whether we can compute the mean, the mode, and maybe the credible interval. And out of the same, you can still test hypothesis, because you can do anything. That's what we said. As long as you are able to arrive at the posterior distribution, then it means it is possible for you to handle any of the estimation cases that may come around or that may come up. So we have this question: assume that the prior distribution for the proportion of defectives produced by a machine is having these values. The value of P, which stands for the proportion, meaning the probability of success here is that the item is defective. So we are given two values of P, either when P is 0.1 or 0.2. Now the corresponding prior values are given, because this is now prior. When P is 0.1, then the prior is 0.6. When P is 0.2, then the prior is 0.4. Denote by X the number of defectives among a random sample of 2. So if you're given a random sample of size 2, then it means you already know when it is defective and it is binomial, then it means since X represents the number of defectives, then the likelihood, because we are not dealing with a sample here, then the likelihood function or the likelihood distribution of our sample data will just be equals to our distribution function for a binomially distributed variate. So in other words, you can call it f of x, or rather p of x is equals to x is given by n combination x, p to power x, 1 minus p, which is the same as our q, probability of failure, to n minus x. So we've already been given here that our sample size is 2. So it means this distribution becomes 2 combination x, p to power x, 1 minus p to power 2 minus x. So the question now you ask yourself is, if the sample size is 2, and you're looking for the number of defectives in this experiment, then what are the possible values of X? When I observe my my items that are being produced by this machine, I know it is possible to get a case where there is no defective item, or there is only one defective item, or there are 2 defective items. So this will be the cases now. Either X is 0, or X is 1, or X is 2. Now, it is out of this that you will be able to come up with the posterior distribution of P, given that X is observed. So you can see, like in this case, it means you'll have quite a number of cases, because you first of all look at, for example, for you to get the likelihood values, you look at the case when X is 0. Get the corresponding posterior probabilities when P is 0.1, when P is 0.2, and the corresponding prior values. Then you go ahead and work on when X is 1 and when X is 2. So it means here you have to look at all the cases. But if, for example, you are told that X is observed to be equal to 0, like in the specific questions we had in the example, you remember, like there is a case where we had the first example we did on discrete data, is where we had you are comparing cross-fertilized plants and self-fertilized plants that are taller. So you are already told 13 out of 15 were already observed. But here now you are just saying generally X is observed. So when you told generally X is observed, you have to look at all the cases, all the options, all the possible outcomes, either no defective item, or 1 defective item, or 2 defective items. So if we can take one of the cases here, for example, suppose X is equals to 0. If X is equals to 0, then our likelihood function here will be equals to 2 combination 0, P to power 0, 1 minus P to power 2 minus 0, which is equivalent to, we know 2 combination 0 is actually 1, P to power 0 is 1, then 1 minus P to power 2. That is what we are left with. And hence, you can now complete your table here, and you can even arrange it in column form. You have your P there, you have the prior values here, then you compute the likelihood values here, likelihood probabilities here. Then finally, remember the arrangement, you multiply your pi of P, that is your prior, you multiply the prior times the likelihood. Then what do you do next? You will get your posterior probabilities here now. Posterior probabilities. Now let's see, maybe with this example, then you can try the others later. So when P is 0.1, P is taking on the 2 values, 0.1 and 0.2. The corresponding prior values, 0.6, 0.4. The likelihood probabilities will be given by this equation when X is 0. So I substitute here. The first one will be when P is 0.1, I'll have 1 minus 0.1 gives me 0.9 U square. And this will give me 0.81. Because we are taking when P is 0.1. Next, when P is 0.2, I'll have 0.2 here. 1 minus 0.2 is 0.8. So I need 0.8 squared, which is 0.64. Then you multiply your prior probabilities and likelihood probabilities. So you multiply 0.6 times 0.81. And this one gives you 0.486. Then you multiply 0.4 times 0.64, and this gives you 256, and so on. Then remember, I'm just reminding you what we did, and then remember you get the product here. The sum of all these, that is the probability, the sum of the priors times the likelihood. So if you add this one, you will get 12, carry 1, you get 14, carry 1, we get 7, 0.72. So to get the corresponding posterior probabilities, what do? You require each one of these products divided by the sum, and then you'll be able to get to the posterior. For example, the first one here will be 0.486 divided by 0.742. Get the answer. The next one is 0.256 divided by 0.742, and so on and so forth. And you'll be through. I hope here you have multiplied correctly and you've done it correctly here. So whichever the case, you should be able to work out this kind of a question. Then after that, you can look at when x is equals to 1, when x is equals to 2, and then you get all of them. So basically, I've already given you a guide on what do you do when you're given such a general case, because you see here you had not been told what is the value of x specifically. So you have to remember from your background knowledge of such examples when you have binomially distributed random variables, then you should be able to know when x is this, then you are able to get the likelihood function directly because it's not a sample. So basically, that is how we would do it. So you can complete that example and try to do the others. And I'm wondering why this one gave us this. This is 486. That's okay. This is 16 1 256. That's all right. And the sum here will be 0.7 or 0.8 something. When x is 0, when x is 1, when x is 2. All right. Then another example, I'm still using the same example, but now I look at a case where suppose the prior distribution of P is uniform now. Now we change the prior. Instead of using the discrete case, now we use the prior, the uniform, a uniform case. So remember, if it's a uniform case where P is between 0 and 1, this is a special case for beta. It's a special case for beta distribution with the parameters 1, 1. Alpha equals 1 and beta equals 1. That's how we take it. When you have a uniform distribution, it is equivalent to having a beta distribution with the parameters 1 and 1. That is, alpha is equals to 1 and beta is equals to 1. But whichever the case, then we know that here you are combining binomial data plus beta prior. So this is binomial data plus beta prior. And we know that this one usually results to a posterior beta, or a beta posterior if you want, beta posterior. So if it is a beta posterior distribution, okay, if it's in the exam, I would have to work it out. But just to remind you what we did, you will take your binomial data, combine it with your beta posterior, beta prior, and then you resort to a beta posterior whose parameters are, but remember, if it is in the exam, you'll have to work it out here. I don't want to work it out because we already worked it out in class. So it will result to a beta posterior whose distribution is our new alpha star will be equals to was it alpha plus beta? Yes, alpha plus x, and then our new beta for the parameter beta for the beta posterior was given by, was it x or n? Yeah, n minus x plus beta. If I do not have a sample, if it's a sample, I would have summation of x here. But when it is directly, it will just be, when it is just a single observation, then this is what I will have. So in our case here, then, I've said here I don't have to work it out because we worked it out in class. I can make a conclusion directly. So it means in our case here, then the new parameter for alpha, or the new alpha, will be given by, we know what is x. We are given, find the posterior distribution of P for the random variable x in question number 1, given that x is equals to 1. So here x is equals to 1, and we already know it is a uniform prior, which we said it's a special case for beta. Alpha is 1, that is beta distribution. Alpha is equals to 1 and beta is equals to 1. Therefore, our new value for alpha will be equals to the original alpha, which was equals to 1, plus the observation x is equals to 1, and this one gives us a 2. So it becomes our new observation for the value of alpha. Then for beta, then it will be equals to our n is 2. We subtract 1. Is it minus 1? I hope so. And then we add 1, where 1 is our beta, and therefore we end up getting 2 minus 1 is 1, or rather this one and this one, and we end up getting 2. So we end up getting our two new parameters, because remember beta is a conjugate. A beta is a conjugate plier to binomial data. So we get a beta posterior with the parameters 2, 2. And that is what the question was all about. Find the posterior distribution for P. And I've said because we have worked it out before, and therefore I can even here write down from previous computations, because we did compute this before, so I don't have to compute it again. So we end up getting that one as our beta. So whichever the case, it means any case, whether it is in discrete nature, that is whether you have discrete data, and then at the same time you have a discrete plier, you can work out such a case. It doesn't matter whether it is binomial, whether it is Poisson, whether it is geometric, or whatever case, you can actually handle such a case. Then when you combine, for example, the discrete now data again, but now you combine with a continuous plier, you can still work it out, because here we have combined now a continuous plier with the binomial data. So any case presented to you, you should be able to handle. Now part 2, which is part B now of our question 2. Remember question 2 we have worked on. Suppose the prior distribution of P is uniform. Find the posterior distribution of P for the random variable x in 1, that is in question 1, given that x is equals to 1 is observed. So here we are saying x is equals to 1 is observed. So we already have that. Now, next, we want to find the posterior mean n mode of this parameter P, which is now solved in question 2. Meaning we are using the beta posterior. We are using the beta posterior. That is what we are making use of. And our beta posterior has the parameters. That is a general one, has the parameters alpha plus x, this one, alpha plus x, and beta that. So we have our alpha star here is equals to alpha plus x, and our beta star here is equals to n minus x plus beta. But we already know alpha is equals to 1 and beta is equals to 1, because now when you're trying to find the posterior mean and mode, it means you're dealing with the general case when your observed value is x. When observed value is x. So we end up getting, this is alpha plus 1 actually. Let me write it here. This is alpha plus 1, or this other one will be our n. We already know our n, we know it's already 2, so it is 2, and then minus x plus 1, so it gives us 3 minus x. So that is what we get as our distribution. So we want to find out generally. Suppose we write down the distribution itself. So the posterior distribution, therefore, posterior distribution will be given by, remember how we write down the posterior distribution? Let me call it P of P given x is equals to, we usually have gamma alpha plus beta over gamma alpha, gamma beta. And then we have P to power alpha minus 1, 1 minus P to power beta minus 1. So if we can substitute, this is 1 and this is 1, so it will be gamma 2 over gamma 1 and gamma 1. By the way, this will reduce to 1, because this is gamma 1, 1 which is 1 minus 1 factorial, that is 0 factorial, which is by convention 1. This is also 1 factorial, by convention is 1. And we know gamma 2 would actually be equals to 1 minus 1 factorial. I mean 2 minus 1 factorial, which is equals to 1 factorial. So actually this is 1. I can even write it as 1 already. So that one will not affect our distribution. That is 1. Okay. Just a minute. Then I'm left with the P to power alpha minus 1. My alpha is my new alpha star is actually alpha plus x. So let me retain the x because I want to assume I'm not dealing with this case now. I'm dealing with the general one here. So my new alpha is actually, forget about this one. Forget about this one first. We only substituted the 2. So it will be 3 minus x, and this one will be equals to 1 plus x. So it means this will give me p to power alpha. My alpha is 1 plus x minus 1. And then 1 minus p to power beta. Beta is 3 minus x minus 1. So we end up getting p to power x, and then 1 minus p to power 3 minus x minus 1 will end up giving me 3 minus x minus 1 will give me a 2 minus x. Beautiful. So that is what I get as my posterior distribution of p given x. That's the posterior distribution for this case. Now, suppose now I take a specific case, because if I wanted now to work out directly, for example, the mean is easy to get because mean we know. Mean is usually equals to the posterior mean. You just get the mean of the posterior distribution. And remember, if I were asked to get the base estimator under the quadratic error loss function or the quadratic loss function, this is actually my posterior mean. But if I were asked to get the base estimator under the absolute error loss function, then I would look for the median. So in this case, the posterior mean is equal to the base estimator under the quadratic loss function or under the squared error loss function. So this is just given by the formula for the mean for a beta distribution, and I'm using the stars because it is my new alpha. So it will be alpha star over alpha star plus beta star. That is the formula for mean of a beta distribution. So in our case, we already know what is this. We already know what are these. The mean for the beta distribution, in our case here, will therefore be given by alpha star. Alpha star is alpha plus x, which is actually 1 plus x, divided by, that is if I substitute my alpha is 1, so it is 1 plus x, it's here. And our beta is here. Let me just cycle them like this. Our beta is that. So in the denominator, I'll have the sum of the two. So we add 1 plus x plus 3 minus x. So the x subtract, and then I'm left with 1 plus x over 4. So that becomes the mean of my my new distribution. That is my posterior distribution. Then I need to get the mode. And by the way, here now, you can answer now this question. Suppose x is 0, is observed. Because remember, our x can take either value 0, 1, or 2. So suppose x is equal to 0 observed. So if x is equal to 0 is observed, then I'll get my mean here will be equal to 1 plus 0, which is 1 out of 4. Suppose x is equal to 1 is observed. X is equal to 1 is observed. If x is equal to 1 is observed, then the mean will be equal to 2 out of 4, which is equal to a quarter. If 2 is observed, then again you can see it will give you a 3/4. And that is how you go about it. But now you have a general case that you can apply to each of the specific scenarios. Then the next thing is to get the mode. So we need to find the mode for these beta posterior. Now we've already seen our posterior distribution is this. Beautiful. So we would want to find out what is the mode, the mode of this distribution. So the question now comes up, how do we compute the mode? Remember, this is a continuous case. So for you to find the mode of a continuous distribution, you remember what we did or what we said. For a continuous distribution, the mode is given by, take first of all the value, I mean it's given by the value of x that maximizes the posterior distribution. Value of x that maximizes. How do I find out what maximizes my distribution? I would need the first derivative. First derivative, then equate to 0. And so this is from our calculus class or from our math classes. Then from there, for you to find out whether it gives you the maximum value, then you look for the second derivative. And here you are looking for the derivative of your posterior distribution. Find the second derivative. Then if your second derivative here of this over d theta or p, in our case here it is p, is it usually becomes maximum when, is it when it is less than or when it is greater than? Can I remember? I think it becomes maximum when the second derivative is less than 0, yes. So when x is less than 0, then, I mean when the second derivative is less than 0, then you have your value of x here is maximum. It gives you a maximum point, or gives maximum point. Yes, gives maximum point when the second derivative is less than 0. So what do we do in this case? Then all you will need to do is take your distribution here, this one here. Now, after solving, you take this distribution and get the first derivative, equate it to 0, solve for x. Once you get your x, then find out whether it gives you a maximum value or a value which is, I mean, a value which is greater than 0 or less than 0. So if you get a value which is less than 0, then that value of x gives you the mode of that distribution. And those are actually the steps that we follow. That is what I wanted to go through. Those are the steps that you'll be able to follow here once you already have these. Remember, it would be a bit difficult if I'm dealing with the normal distribution where you have normal data and normal prior, because the result will be the normal posterior. Now, to find out the mode, it will depend on whether you are dealing with the standard normal distribution, because the other one, to look for the derivative, remember, it might be very cumbersome. But for this one, it's very easy to get the derivative while you have such a scenario. So I believe you can try to go through these later. I'll put this question in the notes as I upload them so that you can also try to work it out and be able to come up with the solutions. The other thing that I just wanted to go over very fast is how would I look for the Bayesian credible? This should be credible level for P for such a case. When we are given, again, the second case here, that we have the random variable x is binomial, the plier is uniform, and here we are told n is still 2, so it is still the same case, and we want to find the Bayesian credible level for P. So what does this tell us? That I need to just find out, remember the definition for this, we had the credible level is actually the probability that our parameter lies between two values, like this, and here it is given, because it's conditional, given the data, that this is greater than or equals to 1 minus alpha into 100%. So what we are supposed to be looking for are these two values. The probability that now your P lies between some two intervals, A and B. So the question comes about now, what do I do when I have such a case. Because in our class, we looked at the example where we had normal distribution. So it was easy to go about it. Now, how do I go about this? It is also not difficult, because all I need to do is to remember my P here lies between 0 and 1. Look at this. P lies between 0 and 1. So this is the range for P. Between 0 and 1. So my values for A and B are somewhere in between the range of P. And therefore, for me to get the probability that P lies between A and B, it means I can work out this I can work out this probability, and it will be help me so for the value of A. And I can also work out this one. It help me again so for the value of B. Because now this one, for this interval between 0 and A and 1A, it's only one unknown A. But you see, when I'm looking for this one, you are integrating from A to B, your posterior distribution, let's call it probability theta given X, d theta. That is what you are integrating. But you see now here you have two unknowns, A and B. But now we are saying, and remember this is equals to 0.05, because it is 95% confidence interval. So you have that. But now, no, 9.5, sorry. 9.5. But now we are saying, for you to solve two unknowns, it will be very difficult. You need an equation where you can solve for A separately and solve for B separately. Now let's see. If from A to B it is 95%, then it means the remaining portion here and the other portion here should be a total of 5%. So if you divide 5% by 2, then here I'll be left with 0.025, and here I'll be left with 0.025. What does that tell me? That if I were to integrate my posterior distribution from 0 to A, my posterior distribution is probability theta given X, d theta, I can equate this one to 0.025, and then I'll be able to solve for A. The other side again, from B to 1, probability theta given X, d theta will be equal to, by the way, it's not theta, it is P, because we are dealing with that, but take your theta to be P, yeah? Because I wanted to be very clear here. Our parameter is P. So if I call my parameter theta so that I don't confuse with the notation for probability. So probability theta given X d theta is equal to 0.025 if I integrate from 0 to A. That is the lower tail of my credible level, this other side here on the lower side. Then the upper tail here will be from B to 1. So if I integrate from B to 1, again, my posterior distribution, I still equate to 0.02, and then I'll be able to get my two unknowns A and B, and that will give me the credible interval for P. So all I need to do is to be able to go about through this one. If I go through this one, I will be comfortable and I'll be able to get the credible level for P, given you are moving from 0 to 1, that is, you are ready for P, and the observed value N is equal to 2, but X is general. In this case, you've not looked for the value of X. It is actually a general issue. You're only working out there the credible level, given the value of how many times have you done your trial, that is N is equals to 2, and then of course you already know what is your prior distribution. It was a uniform distribution. So if you work out these integrals, it will be possible for you to get the value of A and the value of B. And that is basically what I needed to highlight, because the examples we had in class were dealing with the normal distribution. So I needed to take you through this. I will include, I think, this one in the notes. I don't know whether I'll include it when worked out. I will see whether worked out or with the blanks, then you can fill in the blanks because we've already gone through it. But I will include it in the notes when I'm uploading the notes after this class. Right, I think with that kind of a recap, we are okay. We can handle any case now, whether you have normal data, whether you have the other distributions. If Poisson comes in again, you will approach it in the same manner and be able to work it out. Good. So with that now, I want to go to the topic of today. Okay, so we want to go to today's class, and today's lesson or topic is Bayesian decision theory. I've said that one was just a leak up so that we are up to where we are supposed to be, and we get a Mwangi, you are talking. Mwangi, yes, please kindly mute yourself completely. So I'm saying that the topic we're going to handle today after that leak up is Bayesian decision theory. And the objectives are that by the end of this topic, then you as the learner, you should be able to compare decision theory and the frequentist and Bayesian approaches. But if I tell you to give out the differences, you'll be able to. But remember, like we did about the credible interval, under the Bayesian approach and the confidence interval, under the frequentist approach, it's a matter of knowing how to make your description, your interpretation of any scenario that comes along your way. Then the other one is describe the Bayesian hypothesis decision theory procedure. By the way, I don't, yeah, we might have a case of hypothesis, but if it doesn't, I don't know how I came up with this one. It should be Bayesian decision theory procedure. What procedure do we follow? So forget about this one. Identify the components of any decision-making situation and the framework of the loss table. Then solve numerical problems, including or involving either minimax decision procedure, Bayesian decision procedure without data, and risk and loss functions. By the way, there is also the Bayesian decision procedure without data and also with data. That we can handle the two cases, when you are provided with data and when you have no data. How would you be? That is when you have data and when you have data, how would you be able to follow the Bayesian decision procedure and make a good decision out of the situation that you are in? And then, of course, the loss and the risk functions. And of course, under the loss and risk functions, we also look at the risky probabilities and the base risk. There's something we call the base risk here, and base action. So we first of all go through a bit of introduction, and we are saying that statistical theory is a set of techniques for making optimal decisions in the setting of uncertainty. Both frequentist and Bayesian approaches have been developed as far as decision theory is concerned. The definition of a Bayesian decision problem requires the specification of an unknown parameter and its prior probability density function, observed data, if there is any, a likelihood function, a set of possible decisions or actions, and a loss or utility function whose expectation is to be optimized. So it will depend, this loss or utility. If it's a loss, you'd want to minimize the loss. If it's utility is like profit, you would want to maximize. That's why we are using the general term optimize, because optimize may mean either you are maximizing or you are minimizing. So the expected loss can be defined in a number of ways, yielding a frequentist risk, the conditional base risk, and the base risk. So these three are very useful when you want to work on what we call the expected loss in any decision-making scenario or situation. So the goal is generally to select a decision rule that maps the possible observed data to a set of actions so that the base risk is minimized. That is your objective, to minimize the base risk. The goal is generally to select, as I have said, a decision rule. Alternatively, a frequentist may seek to minimize the maximum frequentist risk that might be experienced over all possible fixed values of the unknown parameter, thus yielding an optimal minimal decision rule. So Bayesian method in general is more concerned with the problems of decision making than with problems of inference. Actually, this is what it would be more concerned with, making the decision, optimizing or minimizing. Now, decision theory is concerned with the problem of making decisions well. Statistical theory, decision theory, is concerned with the optimal decision making and the uncertainty or where statistical knowledge is available, only some of the uncertainties involved in the decision problem. So uncertainty could be about two values related to the decisions, or could be about the actual state of the nature. So we basically deal with analytical procedures for the decision-making process. This will involve the selection of an approximation decision from a choice of causes of action among two or more alternatives. The decision theory quantifies the trade-off between the different decisions using costs and probabilities that accompany such decisions. So we consider the situations that involve, number one, a decision maker who has a finite number of causes of action available. Number two, a finite number of possible outcomes or states of nature for each action. And number three, a loss that is incurred for each action, state of nature combination. So the first one, we are saying you have a number of causes of action available at your disposal. Then you also have a finite number of possible outcomes or states of nature for, that is, if you take this action, this will be the outcome. You take this action, this will be the outcome. And then a loss that is incurred for each action. So when I take this course of action, maybe, for example, call it action A1, that is the course of action I take, maybe, for example, it is theta 1. Then I have the state of nature for each action, sorry, action 1, and then the state of nature maybe is theta 1. If I combine these two, what loss do I come up with? And that is the third situation. We are saying a loss that is incurred for each action, state of nature combination. When you combine the two, you combine the action and the state of nature. For example, a state of nature is like the probability, the proportion, all those things. So the decision maker would naturally like to choose the action that would maximize. If the state of nature is known with certainty for each action, and if the corresponding loss is known or can be evaluated, the problem is easily solved. The decision-making process in this case is called decision-making under certainty. Why? Because the state of nature is known with uncertainty for each of the actions, but the corresponding loss is known or can be evaluated. So in that case, we say it is decision-making under certainty. But if only the probability of each state of nature for each action is known, the process is called decision-making under a risk. This is where you'll come in and try to minimize the risk. On the other hand, if a course of action must be chosen without any knowledge of the state of nature, then this decision-making under uncertainty. Let me give a scenario here, or an example, a general example on the decisions, how you need to come up with decisions. A company deciding whether or not to market a new brand of toothpaste with a marketing agent. Clearly, many factors will affect the decision. So you have a company that is deciding whether or not to market a new brand of toothpaste with a marketing agent. And many factors, of course, we expect many factors will affect the decision. So I don't know which factors you would think about. I wish you were face-to-face because you'd give me the solution, the many factors that you would think about in such a case, even before maybe you go over this. Because you're going to the market to market a new product. If you are a frequentist, a classical person, you would go directly and start marketing your product. Okay? You just go to the market because now you've been given this work of being the salesperson to market this new product. So what do? Just take it, go to the market and start maybe selling, start advertising when you are still there and you start selling. But there are very many factors that affect. One of them is you'd think of how many people would want to have this new brand of toothpaste. What is the likelihood of other companies also maybe coming up with a similar brand of toothpaste? So there are very many factors that affect. So we are saying the examples of the factors are the proportion of people who are likely to switch to the new product and the likelihood of other companies producing similar products, that is similar to the paste. So those factors are generally unknown, but estimates can be obtained from the statistical investigations. The classical statistical approach relies exclusively on the data obtained from these statistical investigations, ignoring other relevant information such as the company's past experience in marketing such products. Because it may not be the first time that you're taking to the market a new product. You might have done it before. So the question would be, what experience did you gain when you took a new product to the market? So that now you build on this experience, past experience, as you market your new product. So there are many things that you have to think about, not just about the current data that has been corrected and maybe analyzed statistically, but you also need to look at the past. What experience do you have of marketing a new product, of taking a new product to the market? So we see that statistical decision theory tries to combine other relevant information with sample information to arrive at an optimal decision. Therefore, Bayesian seems to be more appropriate for a decision theory scenario or situation. Why? Because you bring in your past experience and you combine it with the current data, so your marketing strategy might be more effective than a person who just takes the data alone, goes to the field and start marketing the product. Because if, for example, when you're marketing the product, the first time you had a new one and you went out to market it, you never know, you can remember maybe the experience that you got from the customers, from other companies, how they behaved, how they took it, the opinion they had about it. So you will take all that and combine it with now the current situation and be able to be more effective in your new strategy of marketing the new product. So we say that one piece of relevant information that decision theory considers is the possible consequences of the decision. Often those consequences can be quantified. That is, either the loss or gain of each can be expressed as a number, which we call the loss or utility. A loss or utility to a decision maker is the effect of the interaction of two factors, namely, one, the decision or action selected by the decision maker, and then two, the event or state of the world that actually occurs. This is what we are calling the state of nature. So we make some two definitions here. One, the loss function. Remember, we came up with the loss function when we were dealing with Wambo, you have something to say? Mute yourself if you're not talking to us, please. Thank you. So the loss function, I was saying that, remember, we came up with this, we came across this concept when we were looking at the absolute Euler loss function. Absolute Euler loss function, that is during the estimation, the Bayesian estimation procedure. And we also had the other one, which we were calling the quadratic Euler. The quadratic loss function. That is the squared Euler loss function. So we had these two. Now we define it now under the context of the decision theory. But the two of them will still come up when you are making a decision, because you can make the decision under the absolute Euler loss function, or you make the decision under the quadratic loss function. So let A be an action space and A be a member of that action. So we let A, this should be the A, the capital, because it is the action space. So we let A be the action space and a small letter A be a member of that space, be an action, while an estimator theta belongs to the parameter space, the capital theta. Then the loss function divided by this, and this is actually how we also defined it, represents the payoff. So in this case, it is representing the payoff by a decision maker. If he takes A, action A, which is a member of the action space, and the state of nature is D, theta, which is a member of the parameter space. Then we have the risk function and definition number 2. Let A be the class of all decision functions. This should actually denote A. Let D be the class of all decision functions that maps R onto A. So we are mapping the decisions to the action space. So any decision that you make and the corresponding action. A decision that you make, maybe D1 and action 1. And maybe you make a decision 2, and then the action is action 2, and so on and so forth. And let L be the loss function defined on the product or the cross product of the parameter space and the action space. This is the one we said it is L theta A. That's why it is the product of the two, because you are combining the state of nature and the action that you are taking. So we call it now the loss function. So if D is a decision function, then the risk function is defined as an average loss with respect to a sample space and is denoted by. So this is how we define the risk function. So the risk function, which is a function of the theta and the decision, is given by the expected value of the loss function. The loss function is a function of the theta and the decision that you are taking. And remember now here, it means the action will also be taken care of here, which is equals to the integral from x to infinity of your loss function, which is a combination of the parameter, the state of nature, and the decision that you've taken, times the f of x given theta dx. The f of x given theta, remember, this is like the likelihood. This is like the probability function of your data. So it means actually the risk function will come in when you are dealing with a decision making a problem with the data. Because remember, we have mentioned up there in our objectives, you said there are some cases where there is data and where there is no data. So you have to discover when you have data, then you can bring in the risk function, because you'll be able to get the expected value of that. Now, the other one, you see clearly, you only deal directly with the loss function. You either look for the minimum of the maximum or maximum of the minimum, depending on the situation that you are in. Good. What is the general? This one we just go over it. It's very theoretical. The general decision theory procedure. 1, identify the objectives of the decision-making process. Number 2, identify the set of actions and set of possible events, that is states of nature. Number 3, assign probabilities to the occurrence of each possible state of nature, that is the prior probabilities. If more observations are available, then you can calculate the posterior probabilities to the occurrence of each possible state of nature. Then number 4, for each possible event, assign a numerical value to the anticipated payoff or loss of each of the course of actions. Then 5, compute the expected value of the payoffs, or that is either utility or loss function. This could be done either by using the prior probabilities if there are no observations, or using the posterior probabilities. Then the last stage is select the optimum decision among the available courses of action, then maximize the expected value of the payoffs. And I think this is very theoretical. The stages are very theoretical as you go looking at them. But when you get a scenario now and follow these steps, you will be comfortable. And it's just like in your own life, in your own individual life. If I can maybe just digress a bit. If you have any decision that you want to make in life, you have to identify what is this that you want to achieve? What kind of a decision do you want to make? Now, any decisions that you are making, there must be some set of actions available to you. And of course, when you have sets of actions, you also have the consequences for any action that you make. So you put your actions down and the corresponding consequences, so that when you are making a decision on what action to take, then you know, if I do this, this will be the consequence. If I take this action, this will be the. So it means you can also apply these ones in your own life, especially you as young people. It's important to always take care of any action that you take, because any action has its own consequence. So you have to weigh them. Which one is going to be beneficial to me and which one is not going to be beneficial to me? So what are the components of a decision-making situation? So we mentioned the 3 components. One of them is the alternatives through actions or decisions. These are the choices available to the decision maker. They are assumed to be mutually exclusive and exhaustive events. and the decision maker has control over the alternatives. Can you see this? Even in your own life, you have control. There is no way you can give a reason why you did 1, 2, 3 things. You say I had no control over that. No. All the actions and decisions and alternatives that are available to you, you always have control over them. You only need to be above them to be able to control them. So even in this scenario now, for our purpose of maybe this course, we are saying the alternatives and the actions that are available and the decisions that are available to us, we know they are mutually exclusive. If one of them happens, the other one cannot happen. Yeah, and that is true even in our lives. Yeah, there's some things that cannot happen at the same time. You cannot say that you are here and you are there at the same time. If you take this action, that is it. Then you have to bear the consequence for that action. But you have control over the alternatives. The number 2 is the state of nature. These are uncontrollable future events. These ones are not in our ability to change. So they are uncontrollable future events that affect the outcome of a decision. They are outside the control of the decision maker and are also assumed to be mutually exclusive and exhaustive. And then number 3 is payoff. The consequence resulting from a specific combination of a decision alternative and a state of nature as a payoff, and it measures the net benefit for the decision maker. So this is the result of your combination. You took this action under this condition, this is the outcome. You take this action under this other condition, this is the outcome. So we say that payoff can be defined as the quantitative measure of the value of the outcome of an action. So with the 3 of them now, we can combine them to come up with what we call the general framework of the decision process. So in other words, because we are saying you are combining them, so it's like you are taking an action here. Maybe, for example, you have the state of nature here. The state of nature could be in terms of maybe a probability, a proportion. Then you have the action here. Maybe call it action 1, action 2, and so on and so forth. Then you have the probability theta 1, theta 2, and so on. So for example, maybe like in the scenario of taking a new product to the market, maybe the first action here is advertise. Maybe that's the first action that you take, advertise. So what is for example, the cost? You can even call it the cost here, the cost of advertising. So when I take the cost here, the first action is maybe, the first proportion is, or rather the state of nature is maybe say, for example, the cost, the amount of money involved there. The next one is maybe the personnel involved here, and so on and so forth. So when I'm advertising, what is the cost? How many people am I going to use? So the question is, when I take the advertisement, and maybe this is what I'm using now, what is the resulting value here? So you can see finally, I'll have a row table. It's just like maybe in our own life. Think about a case where you are making a decision in the morning, you will carry an umbrella. It might look very funny, but it is actually a case that can come up as a decision-making situation. Carry an umbrella or do not carry the umbrella. These are actions. You're carrying an umbrella, you're not carrying an umbrella. The state of nature and what? It might rain, it might not rain. You see, now you combine them. Okay, let's put it here so that you can see it clearly. So that you can see what I mean by... Okay, my whatever is hanging. I don't know why. Hanging. Let me light it elsewhere. Okay. That's okay. Oh. Okay, sorry. I don't know. All right. It's back, eh? Okay, I wanted to clear this so that I indicate, or I try to demonstrate that scenario. I'm sorry, my power is going off and out. I don't know. I hope it will not interrupt us. So I was saying, you think of a case where you have 2 situations here. You want to make a decision in the morning, carry an umbrella, do not carry. You see, these are actions, eh? Carrying an umbrella is an action. Not carrying is also an action. What is the state of nature here? Remember, we said this one, the actions are controllable. You can control them. They're in your hands. What about the state of nature? Raining and not raining is not in your hands. So here, there will be rain and there will be no rain. So there will be a situation where you carried an umbrella, and when you carried an umbrella and it rained, what happened? You did not become wet, not wet. I'm use NW to represent not wet. Yeah, not wet, okay? Because when you carried an umbrella and it rained, you did not become wet. You carried an umbrella and there was no rain. This is actually a very big loss because, okay, you'll not be wet, but you'll be tired. Maybe use the term tired. Because you carried an umbrella, it did not rain, you became tired for nothing. Then the next action is you did not carry an umbrella, okay? You have not carried an umbrella and it rains. What happens? You become wet. You do not carry an umbrella and then it does not rain. You don't become tired. I hope you can now see. So what we have inside here is what we are calling a loss function. What are the outcomes? When you combine carrying an umbrella and it rains. When you carry an umbrella and it does not rain. When you do not carry an umbrella but it rains. Then when you do not carry an umbrella, it does not rain. You see, you are looking at what are the consequences of your action and a certain state of nature. So remember the state of nature we've seen, these ones are not, they are beyond our control. But the actions that we are to take are within our control. You can control these alternatives. So the alternatives for this case for the action are only to carrying an umbrella, not carrying an umbrella. The state of nature again, but not controllable. They are not in our power to control, in our ability to control. It rains or it does not rain. So you look at now the combination. So what we have inside here is what we are calling a loss function. So it is a combination of an action and a state of nature. And that is basically what I have here in general terms. It has gone down, I think, after there was that interruption. But let's just look at it. So the general framework, we say let A be a set of actions, the class of all actions, of all possible actions available to the decision maker. It is going to rain. I will carry an umbrella, I will not carry an umbrella. Then we rate theta 1, theta 2 up to theta n be the class of all the possible states of nature. It is going to rain, it is not going to rain. N, L, AI, theta j be the loss using action I when the nature of state is theta j. That is a combination of I did not carry an umbrella and it rained. So what is the loss here? I became wet because I did not carry an umbrella, it rained. Or I carried an umbrella, it did not rain. Or I carried an umbrella and it rained. That is now what we are calling the loss of using action I when the nature of state is theta j. So the table is just as I have demonstrated there. You just write it in very simple terms. It's like any other contingency table. You can easily interpret it. So you have the state of nature here. There's the state of nature up here. Then the rows here are representing the actions and so on and so forth. And then inside you have now the combination of them. So we say here that the decision maker is interested in minimizing the loss and therefore would like to choose action AI that would minimize the loss regardless of the state of nature. Usually this is not possible and hence the decision maker must resort to a method that would keep the loss at a minimum based on the amount of available information about the state of nature. So one of the methods that we use is what we call the minimax decision procedure. Generally, some type of information is known about the likelihood of the occurrence of each state of nature. However, in the absence of any information about the state of nature, there are a number of decision procedures available to use. The most conservative of these is what we call the minimax decision procedure. It assumes that the nature is an active opponent who is out to get the decision maker. This is in a very soft way of putting it. Consequently, the decision maker examines the maximum rows that would be incurred for each action and then select the action with the smallest maximum loss. So you look for the maximum of the maximum. For example, consider a decision problem with the table, the loss table below. Sorry, this one went on to the next page, but I think it can be seen, it is visible. So we have the actions here, A1, A2, A3 up to A4. Then we have the states of nature, theta 1, theta 2, theta 3. So the states of nature are, when you are combining with the action, we have a 4. So when the state of nature is theta 1 and the action is 1, then you get a loss of 4. The next one, you get a loss of 5, and so on and so forth. Then after that, you can look for the maximum among each one of them. So under action 1, the maximum loss is 7. It's the one which is here. Under action 2, the maximum loss is 5. Under action 3, the maximum loss is 10. Under action 4, the maximum loss is 9. So what happens is, for the very simple method, that is the minimax, what we are calling the minimax decision procedure, what will happen is, you pick now, you will select the action that would result in the smallest maximum loss, regardless of the two states of nature. So in this case, if you look at them, the smallest maximum loss is 5. 5 is the smallest maximum loss, which corresponds to action 2. So it means you would take action 2 for you to be able to follow now this procedure of the minimax or the maximum, the minimax, minimum or minimax decision procedure. So you pick the maximums, the maximum losses for each of the actions. Then among the maximums, you pick the minimum. So you are talking about the minimum of the maximum. L, A, I, beta, J. So that is basically what you're picking, the minimum of the maximum. Of course, each one of them is at under theta, under theta. We will still revisit this one when we go to the examples for either with data or without data. So we say that this is what we've come up with. Minimum of the maximums is that generally minimax decision procedure should be used only when nature is active and decision makes loss, or if the decision maker is interested in only in keeping the maximum loss at a minimum, regardless of the state of nature. So you just want to make the maximum loss at a minimum to try and minimize the loss. That is what it means. So Bayesian decision estimation, let theta be a member of the parameter space, and theta is a random variable having a probability density function. So you can see now this one brings in a case where you would have data. This is just a definition, then we can go to the specific. Then pi is called a prior distribution. And we write f of x theta as f of x given theta, representing the conditional probability density function of x given theta. Now, since pi is the distribution of theta, then the joint of theta and that is given by that, and we know what this one now results to. This is like the joint. So in this framework, the risk function, remember we defined the risk function up there, is the conditional average loss given by r theta d. That is our risk function of theta and the decision, which is the expected value of that under the theta itself. So given theta is held conditional. So if you look at this one, we are talking about the expected value of the loss function under whichever decision you are making. So in this case, because you can see we have been given the prior distribution, and we already have now the distribution of your random variable, it means this will be a case where data is involved. So we will go to the two situations where there is no data and where there is data. So the two of them will come up. When I have a case like this one here, there is no data. All you have is the loss table. You are making your decision from the loss table. And maybe you can also be given the probability. So you will now bring in the probabilities. But now you see where we have the prior, it means data has already been involved, because now you are updating your current data that you have observed with the prior information that you have. Then you can make a decision out of that. So we make a definition here of what we call the principle of minimax rule. And we say that the principle of minimax estimation is to choose a decision out of the class of decisions, because now D here means it has several decisions to make, decision 1, decision 2, up to whatever value you have there, maybe decision n. So that the maximum under theta, this should have been under theta. I think after changing it into compatible value, the compatible mode, that's when they moved. So this is written as maximum under theta of the loss function, theta d star, is less than or equals to the maximum under theta of the loss function. Remember, these loss functions, not loss, these risk functions, you are calculating the risk function under all the actions, the set of actions that are available. Action 1, action 2, action 3, and so on and so forth. So it means when you compute them, you would need to pick the maximum. If it is a discrete case, it's very easy, because you just pick the maximum among all of them after getting the risk function, which we remember we said it's the expected value, the expectation of the loss function combined with the decision that you are taking. So you'll pick them. Now, on the other hand, if it happens that this loss function is dealing with continuous data, then you'll have to look for the maximum value of your expected value of your loss function. So of course, in that case, you can see there will be some integration somewhere, because now you're dealing with the integration with the continuous data. But for this one, because you'll be adding all of them, you'll have to pick the minimum, or rather the minimum among all the risk functions that you have computed. So I was saying that when computing the risk function under the decision, the discrete cases, then it means you remember to add. When it comes now to continuous case, you'll have to integrate. Just the same thing we did in the first part of the course, where we're dealing with the Bayes theorem, the Bayes estimator, and so on and so forth. You'll have to distinguish when you have discrete data and when you have continuous data. So we are saying in such a rule, the D star, this D star here, exists. It is called the minimax rule, or the minimax decision function. So if the problem is one of estimation, that is A is a member of the parameter space, then we call D star, which satisfies this equation 1, a minimax estimator of theta. So if you're estimating, then it will become the minimax estimator of that parameter theta. So let's look at what happens when I'm dealing with the Bayesian decision procedure with no data. If there is no data, how do I approach this case? And that is all that we are going to look at. Then we also look at what do we do when we have data, and then maybe the examples will come after that. So decision space is the set of all possible actions I might take. We assume that it is convex, typically by expanding a basic decision space D to the space D. This is a capital D of this one, of all probability distributions on the decision space. The parameter space, that is the capital of theta, of possible states of nature, is the one that you are referring to. So this is what you'll be working on. So the loss function L, which is defined as this, L of the decision under theta, which is the loss I incur if I do decision D, and theta is the true state of nature. So if I combine the two, I'm defining the loss function as that. So the parameter space is defined as this. The decision is the set of all the possible actions. So let's see. Then we call delta star minimax if the maximum of the loss function is equal to the minimum of the maximum. If you remember, this is what we did in our example 1 up there. Where we were looking at, you have the states of nature here, you have the actions here, you are picking the maximums up here, and then out of the maximums, we were picking the minimum. So you can see that's an example of a procedure, Bayesian procedure, with no data. But then you can go ahead and upgrade that question that we had and you have a prior probability being provided. So a prior is a probability distribution. Then after that, now you can get what we are calling the base risk. So the base risk of a decision delta for a prior pi is given by this. So now you can see you can now graduate, go to the next level where you are computing the base risk. But if you're just looking at the minimax, then you only look for the minimum of the maximums. So the base risk of a decision delta for a prior pi is given by this, the expected value. I think we've already talked about this. The expected value, where, of course, here you will integrate because it means maybe there is the continuous case. And you can see specifically if the prior has a density, meaning it has a PDF, a probability density function. For finite parameter space, this one, the integral is a sum. Yeah, that is true. Because now you will need to add. You see here, you have been provided with the probabilities. So like the question that we had up there, if the probabilities were provided, then for me to know what happened at action 1, I'll have to add all of them so that I can get the expected value of this one under action 1. Then I go to under action 2 and I do the same, and so on and so forth. So a decision delta is the base for a prior pi if this is what happens. When you have this one as the minimum of this, and of course we've said about that. When it is the minimum, then it becomes the decision. So a decision function D star is known as the base rule with respect to a prior distribution pi if it minimizes the base risk. So when you minimize the base risk, then it becomes the base rule. So a description of all that I have said here, this is just in words, and I don't think we need to go this, but I can just highlight a bit. That suppose that nature is not an active opponent. In this case, the decision maker would want to make a decision based on some type of expectation loss, you see. Now, when we mention expectation, then you know how to get the expected value of any value, because you're just bringing in this one. Now you're looking for the expected value, for example, of the loss function, okay, A theta. So it means you require this one multiplied by the various probabilities that are available. That is the prior probabilities, and then you'll be able to get the expected value of your loss function. So the other question is, but how are these probabilities obtained? So generally, the decision maker would at least have some information about the various states of nature. In any case, regardless of the initial distribution of theta, the decision maker can use the distribution to calculate the expected loss of each action and then select the action with the smallest expected loss. Of course, that is what you'll do in the end, because you've said you are looking for the minimum of the expectations. So this is the base decision procedure, and the probability associated with the state of nature is available from the previous experiment. The procedure of making such a decision is called base decision procedure without data. So in this case, the probability distribution of the state of nature, theta, is called the prior distribution of theta. And the prior distribution is used to obtain the expected loss of each action, and then is selected that which has the smallest expected loss. So we will see, we have an example. In fact, I'll use that question that we had up there with that loss table. We bring in the probabilities, then we look for this, the smallest expected loss among all the actions. Now, what about when we have data? Bayesian decision procedure with data. The decision space is the set of all possible actions, just like up there, that I might take. We assume that it is convex, typically by expanding a decision space, just like we have done in the other one. The parameter space remains the same as the state of nature. The loss function here now has the D, that is the decision that you are making under any state of nature, which is the loss I incur if I do D, and theta is a true state of nature. Now you can see the difference here, add data. The other one, we did not have adding of data, but here we are adding data X as a member of the sample space with a model. So your data has a model, and maybe the model density is f of X given theta. So a procedure is that map that will map the decision, because remember our delta here is the class of all the decisions, that would map this data onto this decision. The function or the risk function for delta is the expected loss. So you can see here now, this one is bringing in, there was no x here because here we were just dealing with the decision that you are making. But now here, we are making a decision based on the data that we have corrected. So we call delta star minimax if, again, the same constant now will come in. The only difference is that here we are bringing in data. We are adding data. So it's like the case of updating data using the other one we were using there. We were using the Bayes theorem. But here now, we are not using the Bayes theorem because we are making a decision based on the data that we have corrected and the states of nature that are available. So in that case now, we are, after adding data, the concept of getting the minimax value will still be the same. The maximum equals to the minimum of the maximum. So applier is a probability distribution. This remains. This one does not change, just like the other case. Now, the base risk of a decision, delta, for applier is given by this. Now, you see the other one, we did not have this. For the other one with the no data, we did not have the prior. But you can now see here, in addition to what we had in the case of no data, we are adding the prior because now we already have the prior information. So if the prior has a density. So for finite parameter spaces, the integral, of course, is substituted with a sum. So instead of this integral, then you'll have the summation L, delta x, and then theta. Then you have your f of x given theta, and you have pi of theta, d theta. So that's the only difference. Just like the other case, you substitute your integral with summation. So a decision delta star is base for applier, actually base list. You can call it base list for applier if the risk function, this one, is less than this one. So the minimum is the one that you pick among all of them for any decision. So a decision delta is known as base rule with respect to applier distribution pi if it minimizes the base risk. That is, this one is the infimum of the other one. And of course, a description like we have done with the no data case, you can look at that description. So the most important thing to note here is that here we are using data. The other one, we did not have data anywhere, but all the others are the same. The other things are the same. The updated distribution is what you actually call the posterior distribution. These are things that we already know now from our previous cases. So once you have your data, you have the prior distribution, then you can get the conditional distribution of x, the probability. That is the conditional distribution of x. Combine them so that you come up now with the, this is the h of theta. That is the posterior distribution. So once you come up with your posterior distribution, then you'll be able to go ahead and work out your case. Look for the risk function, minimize them, and then get the decision or make the decision that you need to make. So basically, the concept is the same. You can see like this one is using the same thing we have used when we had discrete data combined with a discrete prior, because our denominator was a summation. And even here, it will be a summation. But here, remember, you are bringing in a case of the decision and the states of nature that are available. And the many actions, the alternative actions that are available for you. So we say that the expected loss for each action, because now you are taking for each one of them individually, computing individually, and then after that, you can compute the expected value for each. Then from there, you will take the action that results in the smallest expected loss, as of course calculated in the equation above in the Bayesian decision procedure with data. That's fine. I think that's okay. We can make one decision, and then from there I'll jump to one of the examples because I don't intend it to take 2 hours. So just a definition: the base risk or posterior risk of a decision function d with respect to a prior distribution pi of beta is given by this. It is given by the expected value. So we only need to know how do I get the expected value of this. But we know very well how we calculate this. If it's a continuous case, you integrate. And because here we have both x and we have theta, then you'll have double integral. So you integrate over the x's, then you also integrate over the thetas. A different case, so this is when theta and x are both continuous. But when theta and x are both discrete, then you'll have double summation because you are summing over both the x's and the the parameter theta. The other case is when theta is discrete and x is continuous. So if x is continuous, of course, it means you will integrate over the x. If theta is discrete, you sum over the x, and then you will be able to get your risk function. And I think this is very clear. Of course, we know when I have a continuous case and I just combine it together, and I want to integrate out or to remove all of them so that I'm able to get the final function, the risk function or whatever function I'm looking for, I'll have to integrate and both have the summation over the two. Then you have the case where theta could be continuous, x is discrete, then again it will be the opposite. You integrate over the theta, you sum over the x, and that is what we have there. So decision 2, another decision, a decision function D is known as base rule with respect to a prior distribution pi if it minimizes the base risk, this one. I think I had already mentioned this. This could be a repetition. But I have the conditional case that the conditional distribution of the random variable theta given x is equal to x is called the posterior distribution. And you can therefore bring in the distributions now and be able to still get your risk function, because it will be the integral over the g of x. So your g of x is the marginal distribution of your x. Then this is the risk function, or rather the loss function that you have. Then this is the posterior distribution. So when you combine them, you'll be able to get the risk function in that case. And I think with that is enough information on what we are expected to do. So there is an example here. And I think I intend to go through this example maybe, because this is computational. We did this computation in the first part of the course where we were dealing with the posterior distribution. And it's the same thing here. It's only that I've decided to now bring in like it is a new thing, but it's not a new thing. Look at this. The self is the squared L loss function. And the squared L loss function is what we call the quadratic. So it's the same thing, quadratic loss function, which we defined as L. A theta was defined as theta minus, or A minus theta squared. So it is the same thing, but I think I've worked out the same question, but you will just go through it so that now you see how we are defining. Instead of calling this one, you remember this one was our base estimate where we said it's the posterior mean. So instead of calling it the posterior mean, we are actually calling it now our decision. So in that case, the corresponding base risk will be given by this. So you can see it's the same thing, but we only try to bring it into the context, into the context of decision theory, Bayesian decision theory. Because if you look at this one, it's the same thing that we worked out. We went through all these. We had this one. This was our binomial data. Then we came and combined with our prior pi of p. And we were able to finally get the base estimate of p. We worked out this. So we worked out the base estimate of p, which was this. And we were able to work out and came up with the mean of our beta distribution. It is this one, which is alpha over alpha plus beta. And you work it out and you get the same thing. But now in this case now, because we are talking about decision theory, then we are saying the base estimate for P with respect to our posterior distribution of P is now denoted by this. You can now see the difference. We are no longer calling it the base estimator. We are actually calling it a decision now, because it's a decision that you are making. Hence now, put into context, we are talking about the base risk. So your base risk now is this. Why? Because there will be different scenarios for the actions. There will be an action 1, an action 2. Remember the other case, we don't have actions anywhere. But here we have actions. Under action 1, what happens? Under action 2, what happens? And so on and so forth. Then from there, you'll be able to pick the one here, which is the minimum. Because there will be the risk function under action 1, the risk function under action 2. And that's why we have this one here. Because here now it depends on what decision you are taking. so that you are able now to compute this, the risk function at action 1, the risk function at action 2, and so on and so that finally you are able to pick the one which is the minimum. We have an example that we will look at. And I think with that one, we have I've only highlighted what you would do in the former scenario and bring in this. And also an example for the normal, but it's still under the same. You would still follow the same steps we followed in the other one and still be able to come up with what we are calling the base risk. So you will go through these examples, look at them and compare with what we did, and you'll see the concept is the same. It is not going to change. We are only bringing in now the idea of that now I'm dealing with decision theory. It's under the decision theory context. I want to conclude with this example. There are many others that you look at in the notes. Consider the decision problem in example 6.1, the one that we had. Suppose we have now the prior distribution of theta given as this. So these are the prior probabilities. That when theta is theta 1, the probability is a half. If theta is theta 2, the probability was a third. Remember, we had our table written like this. We had the thetas here, theta 1, theta 2. We had the actions here, action 1, action 2, action 3, up to action 4. The thetas were theta 1, theta 2, up to theta 3. What we did there, because we did not have a case where the probabilities are provided, the prior, we only looked for the maximum value under each action, and then we took the minimum of the maximums. But now, suppose now data is, the prior probabilities are provided. Then we are saying we can compute now the expected loss under each one of them. Because remember, we have said in our notes up there, you look for the expected loss under each of the actions, and then, or rather the actions that are provided, the alternatives, then you will pick the minimum of the expected losses. So in this case, you're talking about, for example, when you come to the general case, it means you're looking for the expected value of the loss function, call it this, under in each of the actions. So for example, you come to the loss function under A1 for action 1. So what will you do? You already have the loss here, for example. I can't remember, this was maybe 4, this was 7, and I think this was, let me see, according to here, it should have been 3. You will correct or if it's wrong. So we had, if you take action 1 and the state of nature was 4, theta 1 was 4, theta 1, then the loss function was 4. If you take action 1 and the state of nature is theta 2, the loss action was 7. Now, I've been provided with these probabilities. When theta is theta 1, the probability is a half. When theta is theta 2, the probability is a third. And when theta is theta 3, the probability is a sixth. So for me to get the expected value of the loss function under action 1, then it will be given by a half times the loss function under action 1 plus a third times the loss function under action 1 is 7 plus a sixth times the loss function under action 1, which is 3, and I get the answer. Then I do the same for all of them, and you can see they are here. So we have that one. We have under action 2. We also have under action 3. And we have under action 4. Then from there, you select the minimum. And I have done it here in this table. So you can come and look at the table here. So you have here, this one is supposed to be a half. This is a third. This is a sixth, if I'm not wrong. Yeah, they are like that. So you'll take a half times a 4 plus a third times 7 plus a sixth times 3. You get the answer. You take a half times 5, a third times a half, a sixth times a 4, you get the answer. And then after that, you have all these are the expected values. What do you do with the expected values? You select the minimum among them. And that is now the decision, the base decision procedure leads to the selection of action A4 or action 4, since it has the minimum expected loss. And you get that as the answer. And you can try this example. It's as simple as that one. Type the minimax solution. And I think now we can stop there, but next time maybe we can start from here. We can do example 6.5, and I think we shall be okay. No, but we still have some minutes. We can go up to 9:30. What do you think? Peter, you wanted to talk? Let's stop there. Why, Timothy? You have no more bundles? All of you, bundles. Okay, no problem. I think we can stop there. We've at least gone allowed 1.5 hours. All right, so I think with that one, we can stop there. So up to where we have gone, it is possible for you to do a question in the card. It is possible I give you only one question, but out of that question, you answer all the cases. That is what I intended to do. That's why I wanted to cover now today's lesson, and especially the recap, so that if I give you a question with discrete data, you can get me the posterior distribution or posterior probabilities. You can compute for me the hypothesis. You can do the hypothesis testing. You can also work out the credible interval, both the classical for the same question, and also you compare with the credible interval for the Bayesian approach. Then you can also do now a case with Bayesian decision theory. So we are saying that now you can handle any question. So far what we've done, because what we are remaining is very simple, just looking at the examples of decision theory, either with data or with no data. And then maybe after that, you see what else you are going to do. But something very small is remaining. And I think we shall be done by the end of it all. So I intend to give you the card before the end of the week. Kindly keep on checking, but I also, of course, I would send the notice to the class lab so that you can go to the platform. The card will have some questions, because I've said now this one is a bit, it requires a lot of derivation, but now we cannot derive when we are doing it online at this time. And I don't want to, first of all, give you a question where you'll upload. You'll only upload card 2, where maybe you'll have to do the derivation and everything. But for now, what I intend to do is I'll give you a card that has mixed questions, some that are that involve multiple choice. Of course, there are not many, maybe allowed 10 questions. And the other questions will have numerical answers. So I'll give you clear instructions so that you are able to upload. So the question or the card, I'll give you maybe a maximum of maybe 9 hours in between, but you have only 2 hours to answer. So you'll have to decide within the 9 hours period, which 2 hours do you allocate yourself to answer. And then you submit, and then maybe after 2 or 3 days, you'll get back your result. So I think with that one, we can stop there today. And thank you for coming to class. Kindly continue taking care of yourselves, and rest, continue keeping safe, and pray that all shall be well very soon. Thank you very much, and God bless you.
Goodbye.
Amen. Amen.
Thank you.
Nice
Thank
time.
you. Thank you, and you too.
Amen.
Thank you. Thank you, Kiwa. Thank you so much.
Bless you too.
Thank you. God bless you.
Yeah, have a great day ahead.
And you too, and you too. Thank you, Jeron. Jeron, no, asante sana.
Thank you, madam. Barikiwa sana.
Thank you. God bless you too.